It took about 20 minutes with 5 minutes worth of explanations and checking and verifying and having conversations. So 15 minutes was not an unreasonable time for this quiz. Do you all agree? All right. If you needed more time, that's always available to you. If there's an issue, we can talk about that. Again, for evidence. If you will have these questions, these experimental design, these experimental design questions will be on your on assessments. They're going to be throughout the year. So make sure you're able to do it. If you don't understand, come to tutoring. Today after school, you know the hours. I posted in 3 different places, et cetera, et cetera, et cetera. I'm not going to keep saying that in each of the videos. But just to know that I am here if you need help. I have assistants that understand this very well. All of them understand the idea of independent, dependent variable. And if they get confused, they can come and ask me, and I will explain to all of you. Okay? All right. So now let's go ahead and actually get to some biology, some science, thank God. All right. You had chapter 6. We discussed, that was science 2, but it should have been, I was hoping to get that done a lot faster. And it's not your fault. Technology issues are really frustrating us all. So I apologize for that again. We're all getting through this somehow. All right? So let's go ahead and talk about carbon. Well, let's think about let me see if I have a periodic table in here. I should. I think I do. Oh, no. I should be able to get a periodic. There it is. Periodic table. You guys have seen the periodic table before? Incredibly important. Mendeleev was the person, a Russian, who first put it together. He organized it based on proton number of protons in an element. We can go through all the various experiments, but we just don't have time. If this was a physical science class, it's very interesting how we discovered what an atom was. To give you a little bit of a hint, the ancient Greeks thought, gee, if we keep making things smaller, keep separating, we're going to come to a place that's going to be you can't get things any smaller than that. They called it an atomos or something like that in Greek. I don't know how to say it. Go ask the Greek teacher. But it's an atom, all right? And an atom, they didn't know what it was made of, but they just theorized. Remember, Greeks didn't experiment. They just sat around and thought about things and argued things. And they argued and came up with an idea that the smallest little bit of stuff we're going to call an atom. And over time, these people called the alchemists. Have you ever heard of alchemists? They're people that were scientists and they also believed in spells. So they did a mixture of spells and chemistry. They did experiments, but their goal was to take lead and turn it to gold. Like, wouldn't that be nice? Take lead and turn it into gold. That was what they wanted to do. And so they did. You'd think that that's an insane idea, right? To take lead and turn it to gold. You know, we can do that today. We can take lead and we can make it into gold. Did you know that? It would just cost more than it's worth. We can take any element and turn it into any other element just by adding protons. Because the thing that defines, that Mendeleev discovered, the Russian discovered, is that the atomic number of every element defines the element. So again, I'm really kind of horribly defacing the history of science when I'm kind of throwing out alchemists and Mendeleev and the Greeks, right? I don't have a timeline up. We don't have time for that right now, unfortunately. But to say this, that through this process of humans trying to figure out the smallest little bits, we found out that we can purify stuff. We can take this rock, and we can take the gold out of the rock. It's called ore. We call this stuff ore. We can take gold out. We can take lead out. Gold is fundamentally different from lead. It acts differently. It feels different. It tastes different. Lead is sweet, for instance, which is really bad for babies, because what are babies going to do if they taste something sweet? They eat it. And that's bad for their brains. That's why lead paint is horrible in a house. You move into an old house, the first thing you do is paint it. Not because you're worried about, because of color, not just because of color, but because if you have any babies, you don't want them licking anything, lead, anything. So it turns out that every element's different. And today we know that the elements are classified into non-metals over here. The metals are over here. These are transition metals. These are radioactive. Like each one of these groups have different qualities. Right? We know, you know this. If I gave you a tin ring, a tin earring, would you put it in your ear? I hope not. Because what's going to happen? It's going to turn green. And that greenness that you see is rust. It's when copper rust, it turns green. When iron rusts, it turns red. So when your ear turns green, not because of an infection, but because of rust. Now rust attracts, or it can help tetanus grow. And tetanus is a bacteria that you don't want in your body. Does that make sense? So tin earrings, not a good idea, because that's an open wound, right? I know you don't think of your ear hole, the piercing as an open wound, but it is. And you keep putting metal things in and out, you easily scratch that space. And if it's tin, it can easily get infected. Gold, though, what do we know about gold? Why do we love gold so much? It's even silver to some extent. There's a good reason to love gold. There's actually a lot of great things that gold does that no other element does.
It doesn't rust.
It doesn't rust. It doesn't react. You have a gold ring. This gold ring's been on my finger for 15 years. No rust. That has not been removed from my finger. I think that, well, maybe a couple times. But the bottom line, that gold doesn't rust. It stays the same color. Silver tarnishes, which is a form of rust, but not very heavily. So we like silver as well. The other good thing about silver and gold, especially gold, is it's malleable. You can form it into any shape you want. And you can actually form it, you can pound it into the tiniest malleable. It's a mallet, right? So it's a hammer. So you can, if something's malleable, that means you can shape it with a hammer. You can use a hammer to make a paper thin gold. It acts like paper. What do we call that? Anybody know? It's gold, like your ring. It's metal, but it moves like paper. Yeah.
I don't know if this is right or wrong. Is it like ductile?
It is ductile. That's another word. I'm looking. You shaped it into something. You can shape gold so thin that it acts like paper, like the paper you're writing on. It's flexible. It moves in the wind. What do you call that? Have you ever heard of gold leaf? So gold leaf is just gold that's been pounded so thin that it'll lay down on top of anything and take its form. And you can just smooth it out, and then you can cover anything in gold. So any gold leaf, anything you see gold leaf, is actually a very small amount of gold. It's been pounded into very, very thin sheets. And you can take them off like paper and put them on something. Yeah. Yes. So anyways, gold is a very fascinating metal. It's a good conductor, as most metals are. Some metals are not good conductors. For instance, aluminum, not the best conductor. But still, it's better than carbon. Carbon's not a really good conductor of electricity at all, or heat. So anyways, it's the number of elements tell you what that element is, the number of protons, excuse me, the atomic number. I put atomic number. Atomic number equals the number of protons. So when you look at the atomic number, which is always the smallest one of the numbers on the periodic table, when you look at any kind of atomic number, you're looking at this, 6, 7, 8, 9. Each of these is increasing by 1 proton. 1 proton. We start with the beginning, the first element, the smallest element, and one of the more important elements, this hydrogen, which has how many protons? 1 proton. So the periodic table is well organized that way by, I don't know why this thing is doing this, but it's just one more technological issue to figure out. So it's the number of protons. So when you have a proton number, that would be hydrogen. If you have 2 protons, that would be helium. 3 protons, it's lithium, etc. So lithium's Li, helium's He, and hydrogen's H. In all elements, in all forms of any notation for elements, it's a capital first letter and a lowercase second letter. Capital first letter, lowercase second letter. So you never have like big O, big E, or big H, big E, or anything like that. Then that's not helium. It's big capital first and lowercase second. All right. So those are elements. Now, what about this? What if I had, let me pick one. I like oxygen. It's one of my favorites. So let's go with oxygen. What if I had oxygen with 8 protons? 1, 2, 3, 4, 5, 6, 7, 8. And then I had, I'm going to use the green for a neutron, if that's okay. Remember what a neutron is? Yeah, hopefully from the reading. So neutron means it doesn't have any charge. But it's the same mass as a proton. So it's the same mass as a proton, but it has no charge. So I'm going to go N. Oh, I hate using N, so I'm going to use 0. My zeros are, I need to use a different color too, that might help. Oh, that's no good. It's not. So my zeros have a line through them so you can tell the difference between them and O's, okay? So there's 8 protons and 8 neutrons. Each one has the same mass. We call that mass AMU, atomic mass unit. Oops. AMU, atomic mass unit. So what's the mass of this atom with 8 protons and 8 neutrons? 8 protons and 8 neutrons. 16. So somebody said 8. That's not bad guess. Whoever said it. Okay. 8 wasn't a bad guess. But you're ignoring the neutrons. The neutrons have mass. You're right, they don't have charge. If I asked you what the charge of this thing that I'm drawing out right here is, what would the charge of this be? What would the charge so far be? It would be +8. Why is it +8? Because what's a charge? It's either plus or negative, yeah? Right? Yeah. It's plus in this case, right? So then how many pluses do we have? We have 8 pluses. Does that make sense? All right. The zeros are neutrons. They have no charge. But they do have mass. That's why I put a 0, because they don't have a charge, so they don't impact charge. But they do have mass. So you're right. The mass would be 16. 16. So the mass of oxygen should be 16. Well, there's 2 rules in chemistry, 2 basic rules. If you learn them, and they're going to, like any rule, there are things that change. But if you learn these 2 rules, it will guide you. I'm looking around the room and I see that people are not taking Cornell notes. I want to warn you, if your notes are not in Cornell, you're going to lose points. I keep saying that And it sounds like I'm repeating myself, right? Correct? Because I say things over and over again. Do you know still people argue that I don't say what I've said 100 times? Can you believe that? I can because I've done this long enough, but it just surprises me every time. So when we're looking at oxygen, there's two rules, like we talked with all elements. All elements have this rule. They want to be stable. They want to be at their lowest energy state. And I think all of us understand that. I think every human understands that. You're at home. Your mom's going away to go to work. You're at home on a Saturday. You have a list of things you have to do. How many times have you just sat there and played video games or relaxed, even though you knew you should have been doing something? I'm guilty. I'm guilty.
I'm scared of my mom, so not.
I fear my mother too, but I still try to get away with as much as I could. So that's all humans, all animals, all plants, all life, all non-life. Everything wants to be in its lowest energy state. You put a rock on top of a hill, and it's pivoting on a hill. What will eventually happen to that rock? It'll roll down to the where? To the bottom. Everything wants to be at its rest, at the lowest possible. That's just the nature of the universe. Go restroom? Yeah, go ahead. So it wants to be in the lowest energy state. So there's two ways atoms can be there. One, they have to be neutral. They don't like being charged. They don't like having a charge. If they have a positive, they're not comfortable. I'm using these words inappropriately because atoms don't feel as far as we know. But atoms will react if they have a positive or negative charge. They're not at the lowest possible state. So it's like that rock is at the top of the hill and is teeter-tottering. Would you like to stand underneath it? No, because it's likely going to fall. So these charged atoms are also very much on that edge. They don't want to be there. They need to react. And you don't want to be anywhere near it when it reacts because energy will be released. So neutral. The second thing is it wants a full outer shell. We call that an octet. And we'll talk about why in a minute. And I think the book actually has a drawing of an atom, and their study guide had a drawing of an atom. But those are two things that all atoms want. If they can get those two things, that reaction is going to happen. You're going to get something is going to combine to get that. And we'll see why in a minute. So let's go ahead and draw. I'm going to draw the protons. I'm not going to draw the neutrons. So let's just assume the neutrons are there, please. Is that clear to everybody? I am drawing the protons. I'm not going to draw the neutrons for this discussion. But the neutrons are there. So here's plus, 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 plus. How many in oxygen?
8.
1. And you have a periodic table in your planner, by the way. 3, 4, 5, 6, 7, 8. What's the charge on this? What did we say the charge on this was? 8. So how are we going to get these 8 protons in the nucleus? And by the way, if the nucleus were in the center of Cleveland Stadium, the first electron that would go around this atom would be at the outer edge of the stadium. That's how much space there is between this nucleus of an atom and the electrons. An atom, meaning you, right, because you're made of atoms, is made mostly of space. You're made mostly of empty space. And in fact, that's what, does anybody here watch The Flash? Well, you know how he vibrates and moves through things? That idea came from physics. If you're made mostly of space, theoretically, if you vibrate at the same frequency as something else, you should be able to phase through matter. Yeah.
Isn't that?
Are you going somewhere? You're going home, you say? Did you call the office? Huh? Well, they haven't called. Your mom's downstairs, so you ask your mom to call the office and they can call me. They got to know. I can't let you go until they give the okay. I can't just let you walk out. I'm sorry. Ask her to call the office. Just sit down for a second. You'll be fine. You guys, your parents have to call the office, and the office calls here, as you've seen multiple times, and then you can leave. Yeah.
Isn't that quantum tunneling?
Yeah, in a way. There's a quantum tunneling is a little more complicated, but this is we've not seen it happen. We just know that it's theoretically possible, right? So you're made mostly of space. That's a thought, but I'm not going to draw that much space here. I just don't want you to have this idea that the atom looks like this, because it doesn't look like this. If I was going to draw an atom and I was going to try to be accurate, it looks something like this, okay? That would be what it would look like. And then at the very center in the middle is just this little tiny dot of mass, of protons and neutrons, and that's the nucleus and that's the atom. But there are regions of space that define an orbital. We define these regions. When you're looking at an atom, there's a space around the nucleus where the electrons orbit. They're kind of general. We call it, there's a probability that the electrons will be there. But we draw it as if it were an orbital, like planets going around a sun. We draw it this way. It's not accurate, but it's a good representation. So this would be the electrons. I'm going to draw the electrons with an up arrow and a down arrow, and that's representing the spin of the electron. So there's a physics number that you can calculate. This is spin either up or down. It's not important that you know that, just so you know that's why I'm drawing the arrow. The first shell is called 1. The first shell is 1. And there's only one shape to it, that's S. All right, so there's different shapes. You should know that the S shapes looks like a sphere. You don't need to know that for this class, but it's good to know. That's why we call it an S, because it's a sphere. The others are called a P. The P shells, there's 6 electrons in the P shell. They look like dumbbells. There's 1, there's 2, there's 3, there's 4. Then there's one going in and out of the board, and I can't draw that. So there's one on the y-axis, one on the x-axis, and one on the z-axis, and we call that the p orbitals. So there's 6 electrons in the p orbital. So each shell, except the first shell only has s. So how many electrons can the first shell hold? 2. That's it. It's the only exception. All the other shells, and I can't emphasize enough how simplified I'm giving you this. I'm absolutely simplifying this. So please don't go to chemistry and say, Mr. Mendoza said, this is how it is, but there's more to it. Okay? The second shell, that's right, it'll hold 8, is correct. 2 in the S, and then 6, the second shell has a p orbital as well. So the second shell has an S and a p, where the S has 2 electrons and the p can hold 6. Now, I said oxygen has 8 protons. How many electrons does it have? And how can we tell? If it were going to be neutral, it would have 8. That's correct. Absolutely correct. Great. But it doesn't have 8 normally. It starts off with this number. Here, pay attention, because this will save you so much time this year and next year in chemistry. Very powerful. At the top of the periodic table tells you how many electrons are in its outer shell. These group numbers. 6, 7, 8, 3, 4, 5. Not these. Don't go by these. These don't count. These are called transition elements. They're kind of weird. That's why we call them transitions. These are accurate, though. This is 1 electron in the outer shell. This is 2 electrons in the outer shell. 3, 4, 5, 6, 7, 8. These are filling in what we call the d orbitals. Not important, okay, for this class. The only thing I'm trying to get to is to help you understand what covalent bonds are. So I'm trying to stick to that. All right, so we know there's 6 electrons. How do we know there's 6 electrons in the oxygen's outer shell? How? I just told you. How do we know that there's 6 electrons in the outer shell? How do we know? I just told you a minute ago. I pointed it out. Point an arrow to it. Okay, how about you?
It's at the top of the periodic table. It's like
That's right. It's at the top of the periodic table. I'll give you a periodic table next time we meet. It's at the top of the periodic table. It's the group number. We call it the group number. And there's 6. So let's draw the 6. So there's 1. Again, let me stick to color. 1, 2, 3. They want to be as far away from each other as they can. Why? Because they don't want to run into each other. But what is it? What about them? They're negative. They're all negative, and the same like charges repel. So they're trying to be as far away from each other as they can. So 1, 2, 3, 4. 2 in the first shell, 2s. Then the p shells start to fill in. 5, 6, and that's it. Oh, let me. 5, 6. I put 1 up, 1 down because that helps them get close to one another. Let me erase this. But there's 6 electrons that can form 8. What's the problem here? It's not stable, is it? Even though it's neutral. Because look, 1, 2, 3, 4, 5, 6, 7, 8. There's 8 electrons and there's 8 protons. So what's the charge? What's 8 plus 8 minus 8? 0. Plus 8 plus minus 8. What's 8 minus 8? 0. Okay, so it's a 0 charge. Do you see that? Do you see that? If you're looking at your phone, I'm noting it in my brain. So when you can't answer questions and you're confused, we know why, right?
I'm using my camera.
No, I'm not talking. I see that you're taking pictures. I see that. How are you doing that? Oh, you just took a picture as well? Okay, I was confused. So it looked like he was mirroring my screen. I was like, wow. All right, so there's 8 electrons in total, but there's only 2, 4, 5, 6 in the outer shell. 8 electrons total, which someone said earlier, if it was going to be neutral, to have 8 electrons. You're right, it has 8 electrons, but the outer shell only has 6. Because I was just reviewing what I'd said earlier. I didn't want to bore you by having me say the same thing over and over again. So 6 electrons in the outer shell. How do we get a full outer shell? There's 2 ways to get a full outer shell. Yeah. Yeah, it could take electrons. You could add electrons. They could add 2 electrons, and that would be 8. So that's cool. But what else could it do? Just out of curiosity, it's not going to happen. The one thing that's not going to happen here, what else could it do? Well, that would be the sharing of electrons. But yes, as it could take or share electrons, 2 of them. Correct. Excellent. It would form a bond. You read your chapter. Great job. Or maybe you knew that before you came in. I don't know. Yeah.
Yeah, I was gonna say they form a chemical bond with each other and electron transfer.
That's right. That's right. Now here's my question though. We keep talking about adding electrons. What could it do? Because there's some elements that do something else. That's right. It can give them away. Now this is not going to do that because the 8 protons are too strong. They're going to hold on to those electrons it has. And in fact, it's going to take others. You're correct. It can take 2 electrons and become negatively charged. But I'm more interested in one other example that's very powerful in biology. Let's go ahead and take a look at what happens when oxygen meets hydrogen. Oxygen meets hydrogen. How many protons in hydrogen? I'll tell you 1. And I'll also tell you most of them have 0 neutrons. So that's 1 electron. It has only 1 shell because hydrogen's a small atom. It's actually pretty strong for its size, and there's a reason for that. But there is this 1 electron in the 1s. I hate when my circles aren't close to circles. All right, so that's an S. Don't you hate that when you draw a circle and it looks all wonky? Yeah, it's annoying. All right, so you have 2 hydrogens. Why did I draw 2 hydrogens? Because each one only has, well, you're right, that's where I'm going with it. But there's only 2 electrons. There's only 1 electron in each, see? Because 1 electron plus 1 proton equals 0. They want to be neutral. But how many electrons does hydrogen want in its outer shell? It wants 2. That's right. It wants 2 because it only has 1s. This is the 1s. The 1s only has 2 electrons. It only needs 2 electrons. So that's cool. That only has one electron. And this one needs 2 electrons. So 3 of you said it already. The solution that atoms can come to, if hydrogen, let me be clear. If oxygen took this electron, it would become oxygen -1. It would become a -1 ion. We call those ions, a charged. Does it want to be charged? No, it's energetically unfavorable. It just costs too much. If it took both electrons, it would be a -2. Now these things do exist. We call them free radicals in your body. They actually end up causing cancer and other kinds of health issues. So negatively charged oxygen atoms are just not a good thing in general. And they don't want to be negative, so they find the first thing they can to get rid of those electrons and make those bonds. And it could be your DNA, it could be any molecule in your body, which is why free radicals tend to be so unpredictable, hence the name radical, right? So when we're looking at oxygen and you're talking about making these bonds, they're going to share these electrons. Now oxygen can compromise. By sharing an electron, I wish you'd write stuff down, especially if you don't know answers to my questions. Here, if I'm asking you a question, you can likely bet it's going to come on a test. If I'm asking a question, that's one of the things you can tell. This is important. So these two can share electrons, and these two can share these electrons. All right? Yes.
Jamila's going home.
Okay. All right. Thank you for coming down to get her. Did they? I didn't hear the phone ring, did I? She calls my room all the time. So here are these 2 electrons. Here are these 2 electrons. So here's this oxygen atom. Now it still has, how many electrons does it have in its outer shell? Let's count. 1, 2, 3, 4, 5, 6, 7, 8. 8 in the outer shell, but it doesn't have them permanently because it's sharing. Look, I think of it this way. If I have $1 million, how much does my wife have? $1 million. 0? You don't understand marriage. So if I have $1 million, my wife has $1 million. That's how it works. It's your teamwork. You're sharing. That's what sharing is. I think they need to do a better job in kindergarten is explaining what sharing is. If I own it, my wife owns it too. So these electrons belong to both oxygen and hydrogen. How many electrons around hydrogen's atom? Nucleus. 1, 2. 1, 2. So everybody's happy. Everybody's as energetically favorable as these atoms are going to get. So water, H2O, that's water, H2O, 2 hydrogens. Yep, that's correct. And 1 oxygen. is incredibly stable. These molecules will stay around for a long time. Oddly, we can't break it up. That was my second lab I wanted to do with you guys today, but it's not going to happen. We can break water apart, turn it into oxygen and hydrogen, and we can make a small explosion and turn it back into water again. So we can do that in the classroom with just a battery and a lighter. Easy peasy. Yeah, electricity, electrons. Is it time to go?